My name is Neil Trevett. I am president of the Khronos Group. I'm also vice president of mobile content at NVIDIA. But today I'm representing the Khronos Group, which is an open standards organization that has many different standards that are relevant to gaming development. So I'm going to give you an update on what we're working on at Khronos and what's coming in the near future. So we have a number of topics we're going to cover today in this session. Why standards are important and how Khronos is creating open API standards to let developers get to the silicon acceleration in latest generation mobile phones, the state-of-the-art of 3D graphics APIs, and new APIs that we're working on for sensor and vision processing that will enable advanced applications like augmented reality. And then lastly, some of the standards that we're creating for web and HTML-based applications, particularly WebGL in HTML5, gives the opportunity for portable applications across many different platforms. And all of these slides are going to be posted at the Khronos website, which is www.khronos.org. There's lots of innovation in the mobile space. Mobile gaming is a very active area where there's many new capabilities appearing very quickly now in mobile devices. And there's a number of key innovation areas that we're going to be talking about this morning. The first and the most obvious is 3D graphics. Mobile phones are becoming as capable as current generation consoles in terms of delivering advanced 3D applications. And the API that we use for that is OpenGL ES. Vision is becoming a key part of the mobile experience, using the cameras on mobile devices to do gesture processing, environment processing, feature processing, is enabling a new generation of applications. And we'll talk about how the hardware and the APIs are enabling vision processing. In fact, vision is just one of many different sensors. Mobile phones now have motion sensors, gyros, accelerometers, and many other sensors are coming online to make mobile phones magically aware of their environment. And we are developing APIs to enable application developers to easily get to those sensor networks. And then last but not least, HTML5. The promise of being able to develop a single application that can run on many different platforms. And WebGL is the part of HTML5 that gives access to the GPU for developers within HTML5. So these are the topics that we're going to be talking about this morning. But first, who is Khronos? How many people here have heard of the Khronos Group before? Has anyone heard? John has? Yes, thank you. A few people. Okay, a few people, thank you. So we're actually working hard to make Khronos more visible here in China. There's a lot of activity in China that we think Khronos can help with, and we need China's participation in Khronos to make sure that we're guiding these APIs correctly to meet the needs of the Chinese industry. Khronos is an open standards organization. We are focused on a very specific part of the ecosystem. We're defining APIs that allow silicon to communicate to software. So graphics acceleration, like 3D graphics, vision and sensor processing, general purpose compute, parallel computation, all these things are vital to the games developers using mobile phones. And Khronos is the organization that defines the APIs, the application programming interfaces that the developers use to get into the latest generation silicon. And Khronos, we try very hard not to just document what's happened in the past, but to define the APIs that will be coming in the future that will define the capabilities of the latest mobile devices. So Khronos is an open organization. Any company can join. We have over 100 member companies. The APIs that we are developing now have many hundreds of man-years of expertise built into them, and they're shipping on many hundreds of millions of devices. Any company can join worldwide. We have some Chinese members, not enough. So if you are an active company in the Chinese industry, and what we're talking about here this morning is interesting to you, please consider joining Khronos and being a part of this organization. We have a very good organization for collaboration, including a very strong intellectual property framework that lets competitors come together and cooperate. And probably most important, Khronos has a commitment to royalty-free APIs. The standards that we produce are available to the industry at no charge. There's no royalty to pay. It's because the Khronos members believe that it's better to make money with great products that deliver great end-user experiences using these APIs, rather than trying to charge a small amount for these API standards. So this is a chart of the current membership. So we'll be testing you on this later. The middle ring in the blue is the board of directors. So we have major companies like Apple, NVIDIA, Qualcomm, Intel, and others in the board. But we have 110 companies. There's silicon vendors, software, tools vendors. Unity, that was just speaking, is a member of Khronos, and Unity uses many of the APIs that we produce. Mobile phone OEMs, mobile carriers. It's important that we have many different types of companies so we get the true requirements from the industry. So what are the APIs that we produce? Over the 10 years that Khronos has been in operation, the type of API has changed over the years. The first set of APIs were for the desktop. PCs 10 years ago, PCs and workstations were the key platforms. OpenGL for high performance, high functionality 3D graphics, and then joined by OpenCL for parallel computation. But pretty quickly, 7 years ago, the emphasis began to shift to add mobile devices. Mobile devices beginning to get high performance compute and graphics. So we have the embedded version of OpenGL, which is OpenGL ES, and APIs like OpenMax for video and media streaming, and OpenCL ES for advanced sound or audio. Today, we're developing a new generation of APIs that have two interesting things. One is that we're now developing APIs for input processing, sensor processing, camera processing, vision processing, where most of the APIs before have been output. Graphics is primarily an output API. Also, the APIs that we need to develop today have to work together. Your camera API needs to work very closely with your vision API, which needs to work very closely with your GPU compute API to enable us to build advanced applications like augmented reality. So before, you could have a video API and it would not need to talk to any other APIs. Those days have gone. Everything needs to work closely together. And then the next wave, which we've just started with WebGL and WebCL, that we'll be talking about in a second, is bringing this advanced capability to HTML5 web browsers. So let's look at some of these APIs in each of these generations. The most familiar one, I'm sure, to many people here is 3D graphics, OpenGL. 3D has evolved tremendously over the last 30 years. I'm sure many of you remember Doom on a PC. Now we can run almost photorealistic scenes in real time on standard PCs using the latest generation GPUs. Why have we been able to leap so far in terms of visual realism? It's the power of the GPU silicon. But in turn, that GPU capability is exposed by the APIs. APIs like OpenGL, like DirectX. OpenGL is the open standard API that's available on many different platforms, PC, Mac, and Linux. And we've had 4 generations of OpenGL now on the desktop. The first 2 generations went from fixed function to programmable functionality and were focused primarily on realistic surfaces and textures. The last 2 generations, 3 and 4, have concentrated more on shape realism, tessellation, and soon compute processing that lets us generate very complex and realistic looking scenes. OpenGL has been rapidly evolving over the last 2 years since OpenGL came into the Khronos Group. We've had 6 generations of OpenGL in the last 5 years, and SIGGRAPH in LA is coming up, and keep your eyes open because we're likely to have some new announcements there next week. OpenGL ES-2.0 is the current state-of-the-art API for mobile devices. And OpenGL ES-2.0 was derived from OpenGL 2.0 on the desktop that was originally released in 2004. So there's quite a lot of evolution in the desktop APIs that's available for the mobile industry to use as the mobile chips become more capable. And again, watch out for announcements next week at SIGGRAPH for OpenGL ES. OpenGL ES, even though it's a cut-down version of OpenGL, it has all of the functionality that we need to support some very interesting applications. All of the key gaming engines, like Unity, like Unreal Engine 3, like the Rage engine, are ported now onto OpenGL ES2. It's fully programmable, and today we can support gaming applications that look almost identical, in some cases even better, than the applications that are running on today's consoles. In fact, many people are now building mobile phones that you can use as a gaming console. To use some of the devices using the Tegra 3 device, for example, from NVIDIA. Not only do you get great 3D graphics, you have an HDMI output, so you can plug it into your HDMI TV. You can use a wireless controller, just like you do on your gaming console, so you can get a full gaming experience just using your mobile phone. And I have a short demo here. This is kind of the state-of-the-art of 3D gaming running on a mobile device. This is actually running on the ASUS Transformer Prime, which is a quad-core Tegra 3 based machine. You can see, and this is running at 1080p on an HDMI screen using a wireless controller. I was doing this last night in my hotel room. I'm not a very good gamer, sorry. I keep hitting the wall. But you can see that the water effects, the 60 frames per second frame rate is pretty much identical to what you'd expect on a console. It's actually pretty amazing to think that this is actually running on your mobile phone.
Yeah, that's as good or better than the Wii.
No, it's much better than the Wii. It's up to PlayStation 3 quality. OpenGL ES is a very powerful and enabling API. The good news for the developers is that it's shipping on almost every mobile device. Today, pretty well every mobile device that has 3D capability is running OpenGL ES 2.0. Now, this is some figures from John Petty Research in California. John is sitting right here if you have questions after. And these are some of the figures that show that that market share of OpenGL ES might go down a little bit as the Windows 8 mobile devices ship using Windows RT. Windows 8 and Windows RT use primarily DirectX rather than OpenGL ES. So It'll depend on how much market share Windows RT on ARM processors gets, but these are some current predictions. 80% of the mobile space will use OpenGL ES, and perhaps 20% using Windows RT will use DirectX 11. So it's interesting, it's opposite to the PC, where PC is 80–90% of 3D titles on the PC use DirectX, 20% use OpenGL. In mobile, it's exactly opposite. But for developers, it means you do have to probably cope with both, and so engines like Unity, are a way to hide the differences in the 3D API. Another interesting standard that Khronos has for 3D developers is Collada. Collada is not an API. It's the one standard that we have that's not an API. It's a 3D database format for holding 3D assets. So you can use Collada to import and export your 3D assets from your tools that you're using, that is Maya or Blender or other tools. You can develop some part of your pipeline in one tool, export it, and import it into another, completely keeping all of your assets completely in place. So it's a very flexible format that you can use whilst you're developing applications. Collada is quite widely used. Apple uses it natively in macOS Lion. Google uses it in Google Earth. Adobe is using it in Creative Suite. The CAD industry is using it. It's becoming an ISO standard. There's some interesting open source projects. If you're using Collada or interested to use Collada, there's now an open source importer-exporter called OpenCL. It's quite full functionality. That's now on GitHub, and the conformance test suite for Collada to make sure that you're importing and exporting correctly is also in open source. We'll come on to WebGL, but there's a Collada to JSON open source project from Google that is converting Collada assets into a JSON file format appropriate for use in WebGL. And that, again, is on GitHub in open source if you want to take a look. So there's a lot of activity now around Collada. The next API is OpenCL. C for compute. So OpenGL for graphics, OpenCL for computation. It is parallel processing, and it's heterogeneous parallel processing. OpenCL was created because we realized that CPUs and GPUs were becoming more alike. CPUs have always been programmable, but they're becoming more parallel. 4-core, 8-core CPUs. GPUs have always been very parallel, hundreds of processors, but now they're becoming very programmable. But in the past, you've had to use different software frameworks for programming your CPU code and your GPU code. OpenCL lets you program both types of processor with one set of software. The way that works is OpenCL actually has two APIs and a language. So there's a platform API that lets you interrogate your system to see what CPUs, GPUs, and other processors you have. And a C-based kernel language that lets you write your compute-intensive software in a C-like language, and then a runtime API that lets you distribute those kernels across your GPUs and your CPUs and other processors. So this means you can write one set of code, perhaps an image processing set of routines, or a physics engine, or an AI engine in your game. If you find yourself running on a system with more CPU than GPU compute, you can run those kernels on the CPU. If you find you're lucky enough to have a GPU, you can run those kernels on a GPU, and you don't have to rewrite your software. So you get a lot of portability across different types of systems. There's some interesting projects beginning to use OpenCL. OpenCV is a computer vision library that we'll talk more about later. There's actually some development here in China. Developers are putting OpenCV over OpenCL. They've done about 20% of the functions so far. There's the URL if you want to take a look. The changes are already being folded back into the main OpenCV open source tree. The speed up is quite significant. I mean, some of those functions are going 50 times faster, some of them even going hundreds of times faster. One of the important things about OpenCL and OpenGL is that they can interoperate together. So OpenCL and OpenGL, they can share events, they can share buffers and textures in a very efficient way. So you can use the two APIs for doing compute and graphics that are very closely related. And using the events, that interoperation can be very efficient. This is the number of companies that are currently in the OpenCL working group, a wide variety of companies there. NVIDIA is the chair. Apple is the specification editor for OpenCL. There's some language, Chinese language resources for OpenCL. Morgan Kaufman OpenCL textbook has been now translated into simplified Chinese, and that's available from the Shanghai University Press. It's only been published a couple of months. And there are some case studies from Chinese developers using OpenCL that's been collected and distributed by AMD, and that's available on the AMD website here in China. OpenCL Milestones. The first OpenCL back in December 2008, we've been releasing OpenCL every 18 months. The next OpenCL is going to be a big step forward in terms of functionality. And OpenCL 1.2 is the current version that was released at SIGGRAPH Asia in November last year, so it's just a few months old. I think one of the key things that's going to happen with OpenCL over the next 12 months is you'll see OpenCL beginning to ship on mobile devices. So your mobile phones will begin to get this parallel computation capability, which is going to enable a whole new class of mobile applications to ship that use many hundreds of megaflops of floating point performance. In terms of the OpenCL roadmap, we are working hard on defining a next generation OpenCL that gives significantly more power and flexibility to the programmer. We're also working on an intermediate representation for OpenCL based on LLVM, so we can have alternative languages and code security for OpenCL applications. And then last but not least, OpenCL HLM, a C++-based high-level model for OpenCL, so you can just write a single OpenCL program using C++ in a single source, and the system will take care of a lot more of the housekeeping and parallelization for you. So easier to use than the core OpenCL, less flexible than the core OpenCL. But for many programmers, ease of use is more important than getting the last 10% of performance from a system. So you're going to see announcements from all of these working groups over the next year or two. So let's move on to augmented reality. Augmented reality is a very interesting use case. It uses almost everything in the mobile phone. And if we can get this to work smoothly at 60 frames a second, taking very little battery, then we will have enabled many different mobile applications using vision and sensors and graphics all together. Not necessarily just augmented reality, but a whole wave of context and user-aware applications. So we're using augmented reality as kind of a lighthouse use case. And so what do we mean by visual-based augmented reality? It means that we have a camera that is bringing in a real-world scene. We are using the images from the camera to do feature tracking. So we're tracking objects down to a pixel level resolution using vision processing. We're combining that the camera with other on-device sensors so the device knows precisely where it's pointing relative to the scene, so we can build 3D augmentations, additional information that gets superimposed exactly onto the scene. It's quite a complex thing to do. We can't really do it good enough yet in mobile. So we're working on some APIs over the next year or two to make it really compelling and really high performance. The first one is a very new API. It's our newest API. It's so new we don't even have a logo yet. It's called OpenVL, V for vision processing. It's a hardware acceleration layer for vision pipelines, for gesture processing, for augmented reality, anything that uses the camera as a vision-based sensor. So the problem is that libraries like OpenCV have been very widely used in the industry, but OpenCV is not a Khronos standard. It's a very good set of open source software. OpenCV doesn't have an API. It's about 1,200 functions, and they're constantly changing and growing as the open source community adds more vision capability to OpenCV. It makes it very difficult for the hardware community to accelerate. We mentioned earlier putting OpenCV over OpenCL, a lot of effort. We've only accelerated 20% of OpenCV. OpenVL is a set of vision acceleration API calls that we can use to accelerate OpenCV or other vision libraries or vision applications directly. The silicon vendors, we will all be able to implement that same set of vision API function calls. And then OpenCV will be able to meet us halfway. So we're going to build a bridge from two directions at once. The silicon community building a common set of vision acceleration functions, and high-level libraries like OpenCV gradually being ported over that same set of vision acceleration functions means that OpenCV can be accelerated everywhere. So we're currently working on OpenVL. This is the set of companies that are active in the OpenVL working group. ITSES, which is a company in Russia. It's actually the main company behind OpenCV, is the working group chair of OpenVL. So there's very close collaboration between VL and CV. And we're aiming for a draft specification in 2012, by the end of this year. So camera is one type of sensor, but of course there are many other types of sensor in a mobile phone: gyros and accelerometers, movement sensors, barometers, all kinds of sensors actually about to be built into mobile phones. We need to enable the developer community to have easy access to these sensors. Now, most of the operating systems today, they do expose the sensors, like a gyro or an accelerometer, but the API is very low level. You're almost getting this raw data from the sensor. So for example, the motion sensor inside Android, you just get a set of quaternions, basically a set of matrices as the device moves. So they're quite difficult to process. It means every developer needs to be a mathematical expert. And there's a lot of more subtle processing you need for true sensor processing. One of the trends is you want to use multiple sensors together in a single application. And there's an increasing amount of knowledge and experience from the sensor hardware vendors and sensor middleware vendors on how you should combine the inputs from multiple sensors for the best possible result. So the goal of StreamInput is to provide a sensor fusion API that is high level, that lets innovation at the middleware level to do really intelligent sensor fusion processing, to make it much easier for the application developer to get access to really high quality sensor data. and to make it easy to write applications that are portable across different platforms, even if they use different sensors and different combinations of sensor hardware. So the way that we, well, actually some examples of why you want to do this kind of advanced sensor fusion. If anyone has tried to write a mobile application that uses the compass to try and figure out which direction you're facing, you'll know that if you use a compass inside a room like this, the compass is going to be crazy. You bring it close to a PC, it's going to say the phone is moving when it's not. You walk through a door which has a metal frame, the compass is going to swing wildly. If you use multiple sensors, such as the accelerometer will be telling you that the phone isn't moving in terms of direction, even though the compass is telling you that it is. So if you intelligently combine the accelerometer and the compass, you get a much higher accuracy for your sensor readings. And if you're doing an internal navigation app, navigating around a conference center like this, the barometer will give you height, but it's only relative. So again, you can use the accelerometer to detect that you're moving in a vertical direction, and then use the differential in barometer readings to know how many floors you've moved. And getting these sensor readings at a very low level of power is critical. No one's going to use augmented reality if you turn on augmented reality and your battery goes dead in 30 minutes. We need to use these sensors very intelligently. The gyro is very accurate at detecting movement, but it takes a lot of power because it's a mechanical device that's spinning. The accelerometer is less accurate, but it's not mechanical, so you can use it at any time, taking very little power. So it makes sense to use turn the gyro off, use the accelerometer to detect when the phone starts to move, and then turn the gyro on only when you detect that you're moving enough to need gyro input. So there's a lot of subtlety here that most application developers don't know about and shouldn't have to worry about. We need to give this quality of information to the developers in the standard API. So how does StreamInput do that? We do it by letting the application request high-level semantic information. So if you're doing a Connect type game, for example, you would simply request a stream of skeleton position information. The StreamInput API will then construct a middleware graph that will use the cameras in the system. If you're lucky enough to have a depth camera on your device, it'll use that. If it has a stereo pair of normal cameras, it will use that. Or just a normal camera, it will try and do the best that it can to construct a skeleton data stream and just provide that back to the application through a very simple call, isolating the application from the details of the sensors on the device. StreamInput is also addressing some key issues that all the other APIs so far have ignored. How do you synchronize the sensor data from multiple sensors? So for example, the camera as a sensor has a much deeper pipeline for processing than an accelerometer. If you don't know how the two relate, your motion sensing is going to be very confused. StreamInput puts a timestamp onto every sensor sample, so you know exactly how the various sensors are relating to each other in terms of time. These are the companies that are working in StreamInput. A lot of key companies, for example, PrimeSense is the technology company behind the Kinect, and SoftKinetic is their arch enemy in the market, so that they're both cooperating together at Khronos to build a cross-platform API that gives us access to advanced sensor inputs. We're looking to focus first on cameras and motion devices and mechanical devices, and we're expecting a stable spec in the third quarter of this year. So We have a lot of APIs that can be used for vision processing now. You don't have to use them all, but if you wanted to use them all, they do fit together. So, as you've seen, you can use OpenCL for accelerating vision. OpenVL will be a very good platform for accelerating OpenCV. You can integrate the camera sensor along with other sensors with StreamInput. You can use the camera processing in OpenMax, and you can use the graphics and compute in OpenGL and OpenCL alongside the vision processing. So you can begin to construct a very sophisticated processing platform. So how would you actually use these APIs then in augmented reality? We are now able to see how we can construct an augmented reality application totally using open standards with 100% hardware acceleration. So we've used OpenMax for the camera processing and low-level imaging close to the sensor, such as resizing images and generating a monochrome version of the image from the camera for the sensor processing that would get sent to OpenVL to do your feature tracking. You'd use StreamInput to combine the camera with the other positional sensors. You'd use OpenGL ES, of course, for rendering your 3D augmentations. There's a new extension to EGL called EGL Stream that lets you very efficiently transfer data from the video to the graphics subsystem. And last but not least, OpenCL ES gives you audio processing with full 3D positional audio. So everything that you need for augmented reality is here today. These APIs are here today: OpenMax AL, EGL, OpenGL ES, and OpenCL ES, and will be here next year, StreamInput and OpenVL. Last topic for today is HTML5. So we have many different operating systems in the mobile space. We have Android and iOS, and soon Windows RT. Slightly different APIs across the different platforms. And silicon is becoming cheap enough that it's being built into much more than just mobile phones. Automobiles, consumer electronics, set-top boxes, they're all beginning to get this programmable capability. Developers can't afford to write a different version for every platform. HTML5 is the potential way that we can write a single program that will run everywhere that has a web browser. One suggestion is that we don't reinvent everything. Rather, we take the native APIs that we have already developed and we produce a JavaScript binding for those APIs so they can be used from within an HTML5 browser. And in fact, we started that process with WebGL. WebGL is a JavaScript binding to OpenGL ES, and we'll show you more details. We actually have a second one underway as well, WebCL, which is a JavaScript binding to OpenCL. There are other opportunities. There are web audio standards that could be accelerated over OpenMax. There are the 2D APIs inside HTML5. There's two of them, Canvas and SVG. They can be accelerated over OpenGL ES. And then these yellow blocks are just brainstorming. We could perhaps do a WebVL, a JavaScript binding to OpenVL when we have it completed, to bring vision processing into a web browser very efficiently. And a JavaScript binding to StreamInput could give a sensor fusion API for HTML5 that's actually much more advanced than any of the sensor APIs currently being discussed. And I think you'll see Khronos and W3C beginning to talk much more closely over the next year or two to see how we can best cooperate like this. Let's talk about WebGL. WebGL is actually shipping today. It's a kind of historic opportunity to bring 3D into the browser. There have been previous attempts like Vernal, but they were always struggling to find market acceptance because they needed a plugin. And there was only one plugin that kind of made it, and that was Flash. All the other plugins never really made it that far. The browser vendors, though, have now realized that OpenGL ES2 functionality is pretty well everywhere that they want to ship a browser. So we can create a JavaScript binding to OpenGL ES2, and that browser will be able to run everywhere. We're leveraging a lot of things inside the HTML stack. We now have the canvas tag, which is critical because it lets us write individual pixels rather than HTML graphics for the first time. So we can hijack a canvas and begin to write 3D pixels into it using an OpenGL ES2 binding. And JavaScript is getting fast enough to actually do some very interesting applications. So let's see what's possible. This is how a WebGL implementation will ship. We'll use the drivers on the system. If you're on a mobile system, you'll use OpenGL ES2. If you're on a desktop system, you'll use OpenGL, which is a superset. If you're on a system that has DirectX, Google has an open source project called Angle, which is an OpenGL ES2 implemented over DirectX 9. So even on a system with just DirectX, you can have OpenGL ES. The blue blocks are the blocks that are implemented by the browser vendors. Now, traditionally, that's been the HTML layout engine, the CSS cascading style sheets presentation engine, and the JavaScript engine for interactivity. There's now another block, WebGL. So the browser vendors are becoming a 3D engine themselves. The browsers are now shipping with a full 3D engine functionality built in, with no plugin required. It's a big leap for 3D. Then we have content that uses the WebGL engine either directly using JavaScript or through JavaScript middleware. And there's an increasing amount of JavaScript middleware that makes it easy to develop OpenGL, WebGL content. WebGL is really powerful. It's not trapped in a rectangular window separate from the rest of the HTML stack. It's an intimate part of the HTML stack. You can mix and match 2D, video, and 3D content. For example, you can take an HTML video tag frame and use it as a texture. You can use any canvas as a texture. The Mozilla and Google are beginning to prototype taking a HTML DOM subtree, a web page basically, and using that as a WebGL texture. So you have a web page being shown in 3D, even while it's fully functional, the links and all the animations still working in real time. And in fact, there's one application shipping today that uses WebGL. It's Google Maps. And so if you go to if you're using the Chrome browser, go down to this little box in the bottom left and click Use Maps GL. What will happen then is you'll use WebGL for your maps display. And I have a quick video showing this. So Google are building more and more 3D models into Google Maps. This is the Colosseum in Rome. This is a standard Chrome browser, standard Google Maps. But if you begin to zoom into like the Colosseum here, it's a 3D model that you can rotate around. You can view it from multiple angles. You can zoom further and further in. You transition into an enhanced street view. You can look around inside the model. You can go from place to place inside the model. There's quite a sophisticated warp as you go from point to point in the model. That's all been fully GPU accelerated using WebGL. And you have to stop and remember, this is not a native app, this is a web page. And so the web page is becoming quite sophisticated, and you can begin to see how you can use this kind of 3D functionality for creating web games that go beyond the typical Flash game that most people would be used to. So there's a lot of 3D middleware. There's all JavaScript middleware. On the Khronos website, There's an up-to-date list. It grows every time we do this presentation. So if you don't want to use very low-level WebGL, which is basically OpenGL ES, you can get higher-level libraries that are application-specific and let you get running very quickly. So in how many browsers is WebGL shipping? The good news is that it's shipping now in production browsers from Firefox, from Chrome, on Apple, Safari, and Opera on the desktop. The one missing browser on the desktop is Internet Explorer. We hope that Microsoft will adopt WebGL soon. In the meantime, if you're running in Internet Explorer, you can enable Chrome Frame with one line of JavaScript that invokes the Chrome renderer in the Internet Explorer window that includes full WebGL functionality. And just like OpenCL, I think the big development over the next 12 months is you're going to see WebGL shipping on mobile browsers. So you'll truly, for the first time, be able to write a 3D application and have it run across any desktop and any mobile device. That's really never been possible before. And I think you're already seeing some mobile browsers shipping from Mozilla. The Firefox mobile browser has WebGL. The Opera mobile browser has WebGL. I think you'll see the other mobile browsers with WebGL this year. So WebGL is 100% secure. Obviously, for any web API, security is key. WebGL is architecturally secure. There are no known architectural issues. So it's impossible to access out-of-bounds memory. All that kind of stuff has been fully thought through. We're using WebGL to help harden the GPU against DOS attacks. Any GPU acceleration in the browser can set off a shader that can loop for a long time. WebGL is creating robustness extensions that protects the browser if we hit a long-running shader. The long-term solution is the GPU will become as multitasking as a CPU, but that's not a trivial thing. So whilst the hardware vendors are getting there, WebGL is encouraging OpenGL to provide robustness functionality. One thing that goes closely with WebGL, suddenly there's a need to transport large amounts of 3D data across a network, such as the internet. And it's interesting, the 3D is the one data type that doesn't already have a streaming high compression codec. It's kind of weird, because audio has MP3, video has H.264, images have JPEGs. And as soon as those compression codecs became widespread, the use of that data format really exploded. So once you had audio, MP3, now we had Napster. I put Amazon because it's more politically correct. But Napster was basically created by the availability of MP3s. YouTube is basically created by the widespread availability of H.264. We don't have a codec for 3D, and the 3D industry is going to need it for WebGL. And once we have this codec, it's going to create all kinds of new opportunities. We would want to be able to compress textures and geometry. MPIC has been doing some work on this. Google has been doing some work on this too. The basic idea is that you can have a standard codec that encodes and then unpacks the encoded 3D for use on any client. It's more complicated than video and audio. 3D has more different use cases than 3D, than audio or video. So this is, I think that's the reason why this is happening last out of the four. It's the most complicated. But to begin to solve this problem, Khronos is beginning to reach out to MPEG and to Web3D and others to have a multi-organization liaison to create a royalty-free standard for the 3D codec. The last web API I'll mention is WebCL. So WebCL is a JavaScript binding to OpenCL for parallel computation. Just like WebGL, WebCL stays very close to the original native API, so it looks like OpenCL just in JavaScript. You still write the OpenCL kernels in C, so WebCL becomes a way of distributing native C kernels in JavaScript in the context of a web browser. It's a very powerful programming mechanism. It's different. Intel have a project internally called RibTrail, which actually adds parallel language extensions to JavaScript itself. It's a different approach, but it also compiles down into OpenCL in the end for execution. Now, we're expecting WebCL later this year, but we do have open source sample implementations and prototypes. This is the prototype from Samsung. This one happens to be running on a MacBook Pro. But it's an interesting illustration of the power of using GPU for compute in the web browser. So we start with a standard WebGL application. This is a simple environment with 2 spheres. So this is Union Square in San Francisco. Now, if we turn those spheres into jelly, they're wobbling, there's a lot of floating points needed to do that real-time deformation. Currently, that floating point is running on JavaScript, and although JavaScript is fast, if you throw a lot of floating point at it, it will slow down, so you can see the frame rate has dropped. Now we use WebCL to take all of that floating point off onto the GPU, offloading the JavaScript, putting the parallel computation onto the GPU, so you can see the frame rate jumps right back to over 100 frames a second. So there's a really stark contrast. JavaScript compute on the left, WebCL compute on the right. It's about 100 times faster. Now, it shouldn't be a surprise. GPU is a lot faster than JavaScript, a floating point. But it's WebCL that lets you access the GPU for computation through JavaScript is the interesting thing. And this is a simple demo, but for games, you can imagine using WebCL to accelerate your physics engine and WebGL for your rendering. Some very powerful games are going to be enabled, I think, using these 2 APIs. But why would developers want to use HTML versus native? App stores on iOS and Android have many great native applications, and they're typically really nice, right? An app, it's smooth, it's beautiful, but if you go into your browser, it's kind of horrible little links. But with WebCL and WebGL, you're going to be able to create web apps that are just as beautiful and responsive as a native app today. And a web app has many interesting possible advantages for a developer. It's searchable through Google. You don't need to go to an app store if you don't want to. It's instantly updated. You don't have to get anyone to constantly download your updates to your app because it's just a web page. If you wanted to ship it as an APK on Android, for example, you can compile it down. There are tools to let you compile it down and package it up as an APK if you don't want to run it as a web page. But it is the same code. So there's lots of deployment and discovery advantages to developers through web apps. It's very interesting to see how this begins to interact with the traditional app stores that we have today. So APIs, we've talked a lot of APIs. We're getting close to the end. There's no point having these API specifications if you don't have them shipping on operating systems. But the good news is that both Apple and Android are increasingly shipping more and more of these open standard APIs. And notice the graph here, Android and iPhone together have the vast majority of the mobile market. So a lot of these APIs are available wherever you go in mobile. Android is particularly interesting because it has the NDK, and it enables silicon vendors and OEMs to ship these native APIs in the NDK, available to developers even before Google formally adopts them into the standard platform definition. Now, we want to be careful about fragmentation, because fragmentation is the enemy of Android, but that's why it's interesting to build open standard APIs as early differentiators for the silicon and OEMs, and because it's a royalty-free open standard, we prove how great the apps are if you use these new APIs. It gives the choice to Google to adopt them into their standard platform over time, and we hope that Google continues to do that. But if you're faced today with cross-platform coding, it's kind of interesting. So here, Android, Apple, and Windows RT, slightly different stacks on each of those OSs. Only a couple places do you get a complete connect across. Interestingly, one is native code. You can write C and C++ code on any of those systems. In the 3D APIs, Android and Apple have OpenGL ES. Microsoft is going to have DirectX. So that dichotomy on the PC lives on in mobile. The platform APIs are different, completely different on each one. So Android has Dalvik, which is essentially Java. Apple has Objective-C, which is native C plus Smalltalk. And C# is kind of like Java-ish. So these are the APIs that the platform vendors prefer you use, but it has the most porting effort between the different platforms. HTML5 is another layer that has complete connect, and hopefully soon we'll have WebGL over here, so we'll have 3D with complete connect across into Windows if Microsoft adopts it correctly. So that's the end of the presentation. Hopefully we've taught you today the APIs are key to enabling advanced hardware and enabling new classes of application on a mobile device. But these APIs are no longer living alone. You have input APIs and output APIs, and they all have to work together to enable apps like augmented reality. And we're having increasing cooperation between the native APIs and the web APIs to enable HTML5 soon to do everything that you can do in a native app today. And then finally, as I mentioned at the beginning, Khronos is an open standards organization. Please consider joining the Khronos Group. You would be very welcome. Thank you very much. Do we have any questions? Yes.
So you mentioned that some people, some developers in China, they are accelerating the OpenCV by OpenCL.
Yes.
So you want to have OpenVL.
Right.
So what's the relationship?
Well, that's a great question. So today the best way to accelerate vision libraries like OpenCV is to use OpenCL or CUDA. So we have both types of projects underway. OpenVL, though, is much more focused on just the vision pipeline. So OpenVL is like a hardware abstraction layer for vision pipeline processing. You will be able to implement it using OpenCL. You will be able to implement it on GPUs, DSPs, or CPUs. But I think the key thing that OpenVL will enable, because it's more focused than OpenCL. OpenCL is a general purpose programming language. OpenVL will enable highly pipelined hardware implementations of vision key algorithms. So I think you'll see both. On systems where you don't have dedicated hardware for vision, people will continue to use OpenCL either directly or implement OpenVL over OpenCL. But increasingly, to bring vision processing down to something you can afford to turn on all the time in your mobile phone, which you can't do today, you're going to need dedicated hardware. And OpenVL will enable that as one option. So it's more focused, and it's more tightly focused on enabling hardware implementations alongside OpenCL and other types of vision processing. Any questions?
You define CLADA, sorry.
Yes.
Yeah. So far, WebGL cannot use it directly. It should be converted to JSON, right? So why not? Let the WebGL use it directly.
The question was, why not use CLADA directly with WebGL? Yeah, is that the question? So you could do that. There's nothing that would stop you. But CLADA is not designed to be a transport format. It's XML text-based. It's human readable, which means it's typically bigger than it needs to be. You want to compress it down. So JSON is the obvious first step. A lot of people in the WebGL community are already using JSON, within JavaScript. So the first step would be to have a CLADA to JSON converter. And that's the Motorola Google project that we mentioned, JSON to CLADA, and CLADA to JSON is exactly that. It's a CLADA to JSON converter that puts the scene graph description into a JSON file. It's much more compact, and it splits off the geometry into a binary blob, which is separate from the JSON file, which enables us to go forward to the second step, which is to have the 3D codec, so we can compress that binary blob down. So you can use CLADA, but it's too big. It's a matter of size, and JSON is a much better transport format, and compressed blob JSON will be even better.